These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you. So let's start with this problem, and you can talk me through if you know how you would go about solving this. And since I can't see what you're writing, you should try working this out on paper, but as you're writing, you'll just have to tell me everything you're writing down so I can be on the same page.
Okay.
So what would you write down to solve
first
this?
thing, you need to find out the grams in a mole of H2O. So that would be you have 2 moles of oxygen, sorry. You have 2 hydrogen atoms, and you have 1 oxygen. 2 hydrogen is 2 grams. 1 oxygen is 16 grams. Gives you a total of 18.
Okay.
Yeah, and then you do 18 grams. 18 grams divided by the 30 grams. Is that right?
Okay. So what would you get? Oh, and on the AP test, you're allowed to use a calculator, right?
Yeah.
Okay. So go ahead and use your calculator and get an answer.
Okay. Uh, 0.6.
Okay, all right. So now let's talk that through and get a systematic method for this problem. So basically, all these stoichiometry problems are what we could consider unit conversion type problems. We need to convert between different units. So the way to do unit conversion, first of all, you always want to start by writing down on the right side of your piece of paper your target units. For example, in this case, our target units will be moles of H2O.
Okay.
After you write, so you start on the right side of the paper. Then after you do the target units, you write down what we could call the starting information. So in this case, the starting information is the 30 grams of water. So I'll go over to the left side of the piece of paper and write that. And now we need to convert from these units into these units. And how do you do a unit conversion? Unit conversions always work by multiplying by conversion ratios. So we know that we're going to have to multiply by some fraction. And then the hard part is getting the right conversion ratio. And we need a conversion ratio that converts between grams and moles. So as you take chemistry, you learn more and more different types of conversion ratios. Now this problem, you already knew where to find the conversion ratio. You knew that when you're going from grams to moles, you use the periodic table. So that was good. And so what you got out of that, you said that there was an equivalency of 30, from your periodic table, you saw that 1 mole of water is equivalent to, 18 grams of water. You got that from adding up the masses from the periodic table. It's the oxygen is 16 and 2 hydrogens is +2 because each hydrogen is 1. Okay. Now the next step, and this is where I think this is where a skill that you haven't maybe built yet. Now we have to write a conversion ratio from this. This is what we could call an equivalency, because we're saying these two things are equivalent. That always allows you to write 2 different conversion ratios. So one conversion ratio we could write would be 18 grams water per 1 mole water. But what a lot of students don't realize is that there's another conversion ratio we could write. We could also write 1 mole water per 18 grams water. So every equivalency gives you 2 possible conversion ratios because you can reverse what's on the top and what's on the bottom. And now we just have to decide which of these conversion ratios is the right one to use here. And the way you do that is by remembering that you want the units to work out. So for example, what we want here is we want 1 mole of H2O over 18 grams of H2O. And with practice, the units should make that obvious. How do I know this is right? Because now the grams will cancel, and I'll be left with moles on the left-hand side, which is what I wanted as my target units. So that tells me that this is the right way to set up the problem. Now, the other way you could possibly have done this, and this is kind of what you did, is you could have used this conversion ratio, and you could have done 18 grams of water over 1 mole of water. But if you actually write that out with all of these units, you can see that doesn't make sense, because now the units are not going to cancel, and now you're going to get ridiculous units in your answer. You're going to get, actually, this isn't exactly what you did. You did something different than this. Anyway, this is something else that you might have done. So if you did this way, you would actually end up with grams squared over moles, which is obviously not the target units. So that's the big lesson. There's always 2 different conversion ratios that you could write. How do you figure out which one is the right one to use? Well, just by asking which one will make the units work out correctly. So you can see here that what you want to do is 30 times 1 divided by 18, which is really just 30 divided by 18. Go ahead and do that in your calculator, and let's see what you get.
1 2/3.
Yeah, so we could say the answer is 1.67 moles of water. Now, I think what you actually ended up doing is you did 18 divided by 30, just doing the division in the wrong direction. And this is just related to what you said at the start. You said that what was giving you trouble was setting up the math, and that was what messed you up, setting up the math ahead of time. So basically the thing to do here is if you kind of follow this method, then the math will be set up. So the key things you could have done to get this right, first of all, write the target units. Then write the starting information. Then identify the 2 possible conversion ratios. There's always going to be 2 possible conversion ratios. Then step 4, you figure out which conversion ratio will work for the problem that you're working on. And with practice, this should eventually be kind of mechanical, but it takes a little practice to get there. Okay, good. So that would be an example. Does that example make any sense?
Yeah.
Okay, good. All right, so we should try a little bit more practice with that. And one thing I should say is, as we're going through the tutoring session, the main purpose of the tutoring session is to give you problems to practice on your own. So you want to be careful to write down every single problem we do as we're going, and then you need to go back and try those again on your own later. So after the day's session, you should try this problem again. You should try to organize your notes so that you'll be able to look at the problem and still cover up the solution. So you can still go back and do the problem again later, because these are problems that you're expected to be able to do so quickly on the actual AP test that it shouldn't take you much time. So it's really important to practice those. All right, so let me give you another problem. Let's say that we have 50 grams carbon dioxide is how many moles? Okay, so I'd like you to try working out this problem again on paper. You should write this down on paper. And as you're doing that again, please tell me what you're writing down. And try to use the method that we were just talking about.
Okay, so let's see. So we need to find out how many grams are in 1 mole of carbon. That looks like it is going to be 44, I think. Yeah, 44.
Okay.
So then you just do 50 grams of carbon dioxide times 1 mole carbon dioxide over 44 grams carbon dioxide, which gives you 1.14 moles.
Okay, good. That's right. Now, that's good. Let's just try to be a little bit more systematic in doing these problems. Now, you might already feel that this is so easy that you don't need to be systematic with this, but what we're going to do next is keep doing harder and harder unit conversion problems. And as they get harder and harder, it's more and more important to be systematic. So even on these really easy problems, let's be systematic. So what we should have done first was write the target units. First, you write the target units on the right-hand side, which is moles of carbon dioxide. Then you move over to the left-hand side and write the starting information, which is 50 grams of carbon dioxide. And only then does it make sense to come up with the conversion ratio, because if you haven't identified what units you're starting with and what units you're going towards, you don't really know what type of conversion ratio you need. And you came up with the right conversion ratio, moles of carbon dioxide over grams of carbon dioxide. So I guess you looked this up in the periodic table and you saw carbon has a weight of 12 and oxygen is a weight of 16. So this would be 12 plus 2 times 16, and that is 44. Also, you should always physically cross off the units that are canceling to double check that you're doing this correctly. And then you saw that the answer was 50 divided by 54. So you got the right answer, and you are understanding this correctly. But like I said, we want to build up a systematic method so that we can do the harder problems. So even though this problem was pretty easy, we want to be in the habit of writing each step down. But it looks like you're already getting the idea. So that's another problem in your notes to try again later. So let me give you another problem. Let's say that we've got 4.6 moles of N2. So when you're ready, again, try to work this problem out on paper and tell me what you're writing down. And try to be systematic and go through each of the systematic steps we were talking about before.
Okay, so first thing, you write down your target unit. Second thing,
What
you
are the
write what we
target units?
know, which is going to be 4.6 moles,
Good. By the way, what did you write down as the target units?
grams of nitrogen.
That's right. Good.
Okay. Then you look how many mole or grams are in 1 mole of nitrogen, which is 14. So you do 4.6 moles of N2 times 1 mole N2 divided by 14 grams of N2, which would give you no, I've done it wrong. It should be 14 grams of N2 over 1 mole of N2. Yeah, which gives you 64.4 grams of nitrogen.
Okay. Let's see. 4.6. You said 64.4? Okay. Okay, so let's talk through those steps. You started by writing down the target units. That's good. Then the starting information. And then we have to get the conversion ratio. How did you get this number 14?
I looked on the periodic table.
And the number, the mass of a nitrogen is 14.
Yes.
But wait a second.
Oh, no, it should be 28, shouldn't
Okay,
it?
there you go. That's right. Okay, so let's fix that mistake and try again.
Okay. Now you have 128.8.
Okay, so instead of 14 grams, this should be 28 grams. And then we would get 128.8. Good. Because as you're seeing now, each molecule has 2 nitrogens. So if one is 14, 2 would be 28. So that was just a careless error, probably. You did that correctly on this problem. Here we had oxygen. Oxygen weighs 16, but you didn't use 16, you used 32, because there was 2 oxygens. Sometimes people are less likely to see that for some reason if there's only one element. They just ignore the subscript. But even though there's only one element, this is N2, not just N. Okay, so that was a mistake. Good. And then the other mistake you made, you caught. And this is why I was talking about why it's important to be systematic and write each step down. So how did you know that your first approach here was wrong? Well, you can see it's wrong because the units won't work out. If you work it out this way, you're going to get bizarre units of moles squared over grams, which is obviously not what we want. That's probably how you saw you were making a mistake. So instead, you want to do it this way. And again, you should be physically crossing off the moles here to confirm that the units really are working. So again, when we started, what you said you had trouble with was setting up the problem. And this might be kind of a simple example of what you meant by that. All these unit conversions usually involve either multiplying by a number or dividing by a number. And students just have a hard time knowing when they should multiply and when they should divide. For example, here you started by saying that you were going to divide by 28, but then you figured out that was wrong and that you should multiply instead. And so the answer to your question, how do you know how to set things up? By carefully writing down all the units. With practice, the units are supposed to make it easy and automatic to see whether you're multiplying or dividing, and they're supposed to make it easy and automatic to see how to set up the problem. So that's the method we'll keep working on, using the units to make that easy and automatic. Why did you write this with 1 mole on top and 28 grams on the bottom to start with? Probably because that was the type of conversion ratio you needed for the 2 previous problems. Sometimes people get onto autopilot and they assume all the problems are the same. But remember the lesson we saw in the first problem, there's always 2 ways to write the conversion ratio. There's always 2 ways to write the conversion ratio, and you have to figure out from scratch for every single problem which is the right one. You can't just assume that the way it was on the previous problem is the way it's going to be on this problem. So you caught that mistake, so that's good. Okay, and then we have to watch out for these subscripts as well. All right, so let's say that we've got, let's see, 11 moles of O2 is how many? All right, well, again, work this out on paper and tell me what you're writing down.
Okay, so first you write down your target unit, which would be grams of O2. Then you write down what you have, which would be 11 moles of O2. And then you find your conversion ratio, which would be times 16 grams of O2 for every mole. No, do it again. 32 grams of O2 for every mole. And that would give you 352 grams.
Of O2. Okay. You started by writing the target units, then you wrote the starting information. By the way, one thing that it sounds like you're doing, which is important, is that you're not just writing the units, but you're also writing the substance. That turns out to be really important in chemistry. If you had done the problem like this, that wouldn't really be very good. It's not good to only write the units. When we say that you're writing the units, we almost always mean you have to write the substance as well. So it's good that you're already building that habit. And then you had to get the molecular weight. So each oxygen is 16. So if there's 2 of them, that would be 32. It sounded like at the start you were just writing down the 16, but you caught your mistake. So that's good. And so then you did the multiplication. We should physically cross these out so we can see that we set this up correctly. And then it comes out right. So you can see it's easy to make careless mistakes in these problems. That's why I was mentioning it's just important after today's session to go back and do all the problems again so that you get to the point where these problems are easy. These are problems that have to be quick and easy for us, and that we have to be confident that we're not going to make any careless mistakes. Now let's just briefly talk about why this works. Why is this the right method for doing unit conversion? Well, suppose that you had, say, the number 1/2, and you wanted to change it into quarters. How would you figure out how many quarters are in 1/2? Well, you would do this. You would multiply by 2 over 2. 2 times 2 is 4, and 2 times 1 is 2, and then you would see that 1/2 is the same thing as 2 quarters. 1/2 really equals 2 quarters. So the point here is just because things are written differently doesn't mean they represent different things. Now, why does this work? Why is it that why can we multiply this without changing the number? Because we're really multiplying by the number 1, right? When you multiply by the number 1, things don't change. What's 1 times x? It's just x. So by multiplying by the number 1, we know we're just getting a different version of 1/2, but it's still the same number. Well, if you think about it, that's what all of our unit conversions here are based on. Because remember that this conversion ratio comes from an equivalency. You know from the periodic table that 32 grams is equal or equivalent, 32 grams of oxygen is equal or equivalent to 1 mole of oxygen. So, but if those both represent the same thing, then 32 grams over 1 mole is really the same thing as the number 1. 32 grams of O2 over 1 mole of O2 could be considered just like the number 1. That's why this number and this number represent the same thing, just like these two numbers represent the same thing, because we're just multiplying this by a version of the number 1. What's the point of multiplying by 1 if it doesn't change anything? Well, the point is you can see that from fractions, even though multiplying by the number 1 doesn't change the essence of the number, so to speak, it changes the way the number is written. So it's a way to change the form without changing the essence, so to speak, of the number. I think that's important to understand the basic rationale behind unit conversion. For example, a lot of the times you want to check your work and make sure you're using the right symbols. A lot of the time when people are doing this, I see them put an equal sign here. But that obviously wouldn't make any sense at all. We're not setting these two things equal to each other. We're multiplying them times each other. Just like here, we're not setting these two things equal. We're multiplying by the number 1. So you want to go back and check your work and make sure that you're actually putting a multiply sign in each of the examples that we did so far. Otherwise, this whole method wouldn't make sense. The equal sign goes over here. Here's the equal sign, just like the equal sign goes here and the multiply sign goes here. So by understanding, so the basic idea behind unit conversion is that we're just multiplying by the number 1 to change the form of the number without changing the essence, just like when you're changing denominators and fractions. By the way, that also shows why you could always write a conversion ratio 2 different ways. That shows why these are both possible conversion ratios, because the top and the bottom are the same thing. So if 32 grams of oxygen over 1 mole of oxygen is equivalent to the number 1, then 1 mole of oxygen over 32 grams of oxygen would also be equivalent to the number 1. So that shows why it's legal to flip the top and the bottom. The reason we can flip the top and the bottom is because they both represent the same thing. You can't like flip 1/2. 1/2 is not the same thing as 2 over 1. But you can flip these because they both represent the same thing. You just have to decide which version of the conversion ratio is more convenient for the problem that you're working on. All right, so let's summarize what we've seen here so far. What we've gone over so far was how to convert between moles. Let's call this a conversion table. Conversion ratio table. Now what we've learned so far is how to convert from grams of X into moles of X, where X is any substance. So we could go from grams of oxygen to moles of oxygen, or grams of water to moles of water. Where do you get the conversion ratio that you use for this conversion? Well, you already knew that before we even started today's session. You already knew that you get this conversion ratio from the periodic table. The conversion ratio here comes from the periodic table. You already knew that, I think. You were just having trouble understanding how to use that to solve problems. Okay, so I think we made good progress on that. So let's go on to another type of problem here. Let's see. So let's say we've got let's say I have 537 water molecules. Let's make this. Let's say that I have 8 times 10 to the 25 water molecules is how many moles of water? Have you seen this concept of a mole yet in your course?
Yeah.
Yeah, okay. Well, let's see whether we know how to do this problem yet. So try working out this problem on paper. If you get stuck, I'll give you some help. But first, try it on your own. So tell me, what would you write down to solve this problem?
First thing you do your target unit, which would be moles of H2O, and then I guess you write down what you have, which is 8 times 10 to the 25th molecules H2O, and then you would need to write down your conversion ratio, but I don't know what that would be.
Okay. Do you mean you don't know how to figure out what it would be, or you don't? You just don't have it memorized?
I don't have it memorized. I
Do
don't
you know how
think.
to
I
do you
don't
know
know.
how to do you know how to figure it out?
Well, no.
Okay, sorry, that was
Just,
a
oh,
weird
wait,
question.
hold on. Would you do grams? So if there are 808 times 10 to the 25th molecules, then there would be two H2O, two hydrogens, one oxygen.
Okay, let me help you with that. That turns out not to be the right path. That was kind of a weird
This
question.
is
All right, so let's just go through together how to do this. So why can't you just do this problem the same way as the previous problem? Because we've got different units. The previous problem was going between grams and moles. So we know how to do that, but this is a different type of conversion. Now we're converting between individuals and moles, individual molecules and moles. So we need to learn a new place to get the conversion ratio. This conversion ratio doesn't come from the periodic table. Well, I think you mentioned that you've seen this concept of a mole in your course. Do you know what is a mole? What does the word mole mean?
is how many grams are in to 22.4 liters of that at 0 degrees Celsius. Is that right?
Can you say that one more time?
It is how many grams of that substance there is in 22.4 liters at 0 degrees Celsius.
Okay, that's not quite right. It would be better to say it's the number of molecules, not the number of grams in 22.4 liters. And then that would be correct. All right, but there's actually a much simpler way to define it. Let's give it a much simpler definition. Let me ask you another question. What does the word dozen mean?
12.
Okay, so the word mole is like the word dozen. It just is a number. Do you happen to know what number a mole is?
The number. No,
Okay, so
no,
let's
I
go
don't.
through that. And do you have your textbook with you?
Yes, I do.
So usually in the textbook, there's usually a bunch of constants that you need on the inside front cover or the inside back cover. Can you take a look at the cover there? Do you see something that's like a table of physical and chemical constants?
Sorry, can you say that again?
Sure.
Your mic is cutting out sometimes.
Yeah, okay, I'll try again. Take a look at the inside or the back cover of your textbook. There should be a table of constants. Things like the mass of an electron and the ideal gas constant. Do you see a table on the inside front cover or the inside back cover of your textbook that has a bunch of constants?
With like Avogadro's number, atomic mass, unit charge of an electron, that kind
Excellent.
of thing.
That's the right one. So it turns out another name for mole is Avogadro's number. So what is Avogadro's number according to that table?
6.02214 times 10 to the 23rd per
Good.
mole, I guess.
That's right. So let me write that in a way that'll be more useful. So the conversion ratio here is 1 mole of X is equal to 6.02 times 10 to the 23rd individual X. So basically, remember the word dozen means 12. Dozen means 12. The word mole means 6.02 times 10 to the 23rd. That's approximately what it equals. So just like the word dozen means 12, the word mole means 6.02 times 10 to the 23rd. Or just like the word hundred. What does the word hundred mean? It means this. So the word mole is just a name for a big number. The word mole is just the name for a really big number. So here's the really big number that we're using. Okay, good. And this then
Okay.
gives us a conversion between these types of concepts. We can go from moles to X and vice versa. The way I would read this is 1 mole of X equals 6.02 times 10 to the 23 individual X's. I'm not going to write down the word individual, but I mean individual. Just like you could say 1 dozen eggs equals 12 eggs. And you can read that as 1 dozen eggs is 12 individual eggs. Or, whoops, 1 dozen cats is 12 cats. But I would read that as 1 dozen cats is 12 individual cats. Okay, even though we don't need to write down the word individual. So that gives us this conversion ratio. So mole is just a number. Is a mole a very big number, or an ordinary sized number, or a very small number? Would you say that 1 mole is a very big number, or that it's an ordinary sized number, or that it's a very small number?
It's a big number.
Yeah, because 10 to the 23rd means 6 followed by basically 23 zeros or decimal points. So this is a huge number. Okay, so there we go. So that's the best definition of a mole. That's really important to keep in mind because you'll need to keep using this. I'm not sure whether you're expected to have this number memorized for the AP test or whether they would give you it for each problem. Like I said, I haven't looked at an AP test before, but when you take tests in your course, do you get to use notes, or does the instructor expect you to have everything memorized? In your class, are you allowed to use a cheat sheet or notes when you're taking tests, or does the instructor expect you to have everything memorized?
Well, it depends on the test. I think the only things that we don't have to have memorized is going to be the activity series and the periodic table, and that's just about it.
Sure. Okay. Well, so maybe eventually it's a good idea to memorize this number. But I did want to point out to you, if you ever forget this number, you can look it up in that inside cover of your textbook. Remember, what's another name for a mole? Avogadro's number. Just like the word dozen means 12, another name, Avogadro's number, basically is a synonym for the number, this number. But notice that the way they wrote it on the back cover is maybe not the most useful way to think about it. They wrote it as Avogadro's number is 6.02 times 10 to the 23rd per mole. That's not the most useful thing for solving problems. For solving problems, you want to use this equivalency. Okay, so now let's try to apply that to this problem. Now you already wrote down the target units and the starting information, so all I have to do now is put in the conversion ratio. So what do you think? What conversion ratio should we use here? What should we write on the top and the bottom?
1 mole. Would it be 1 mole over Avogadro's number?
Good. Whoops. Now let's be a little more systematic with the units, though. On the bottom here, we should be writing 6.02 times 10 to the 23rd individual waters. And on the top, we should be writing 1 mole of water. You don't have to write down the word individual, but this is the good way to write it out. So the way I would read this is 6.02 times 10 to the 23rd individual waters. And I would read this as 8 times 10 to the 25th individual waters, or individual water molecules. And this is 1 mole. How did you know to write the conversion ratio this way? Because now the units will cancel the way we want, and we'll get moles as our answer, which is what we want. So now what's the calculation we have to do to find the answer?
It's going to be 8 times 10 to the 25th divided by 6 times 10 to the 23rd. And then I got 133.3.
Okay, I got something a little different. I probably rounded differently. If you use 6.02, I think you get 100. Well, I could round it off to 133. So we both got 133. Okay, good. Okay, so that's the way to do this new type of conversion. So for this new type of conversion, we need this new conversion ratio. which you can get, if you forget this number, you can get it from your back cover. And maybe now you can see, maybe now it makes more sense what I meant by X. For any particular problem, you're not going to write X, you're going to write the individual substance. So for example, in this case, we had that there was 1 mole of water, which is equal to 6.02 times 10 to the 23rd individual waters. So for each problem, you have to decide what's the right substance X to put in. Okay, so that's another type of problem that we've learned how to do. So that would be another important example to have in your notes and go back and try again. So let me give you another problem. Let's say that we've got 5 times 10 to the 24th carbon dioxide molecules is how many moles? So try working this out on paper using the systematic technique we were just talking about, and tell me what you're writing down.
So first thing you do is you get your target unit, which is going to be moles of CO2. Then you write what you have, which is 5 times 10 to the 24th CO2 molecules. And then you do your conversion ratio, which is going to be 1 mole of CO2 for every 6.02 times 10 to the 23rd moles of CO2. Okay, and then, oh wait, no, sorry, no moles on the bottom. Okay, so then it's going to be 5 times 10 to the 10 to the 24th divided by 6.02 times 10 to the 23rd. I got 8.31.
Okay, good. So I'll round that up to 8.3 moles of carbon dioxide. So you started by writing the target units, then the starting information. You figured out the conversion ratio. Okay, good. And so that would be a correct way to do this problem. By the way, one thing you always want to do is get into the habit of maybe making a prediction before you do the problem. Something we could have predicted before we did this problem, well, just by looking at this number, you can see, do we have more than a mole or less than a mole of carbon dioxide? More, because how much would 1 mole be?
6.02 times 10 to the 23rd.
That's right. Just from looking at this, you can see that we have more than a mole, so we could already have predicted going in that we're going to get more than 1 mole. It's always a good thing to get a little bit of a prediction before you start, or at least to check your answer to make sure that it makes sense. So we can see this makes sense because we knew that we had more than 1 mole of the substance as we were going into the problem. Okay, good. So that was the correct method. Let's say that we've got 2.7 moles of nitrogen is how many molecules? Let's try this problem.
Okay. First thing to do is write down your target unit. Use molecules of N2. And you write what you have, which is 2.7 moles of N2. Would you have to multiply Avogadro's number by 2.7 first?
Let's see.
Yeah, right?
Tell you what, keep working on this on your own a little bit. Take your best guess, and then I'll give you some help after you've given it a try. So take your best guess as to what would you write down to work this out?
Okay, so 2.7 moles of N2 times 6.02 times 10 to the 23rd N2 divided by 1 mole of N2, which would be, let's see, 2.7 times 2. I got 1.6 times 10 to the 24th.
Okay, you wrote the target units, then the starting information. And then you asked me a question. You were asking, I think you asked something like, do I need to multiply the 2.7 by Avogadro's number before I do something else? I wasn't quite sure if I understood that. We did end up multiplying 2.7 by Avogadro's number. We did multiply 2.7 times 6.02 times 10 to the 23rd, but that wasn't like preparation. That wasn't something we did before solving the problem. That's just the way to solve the problem. That's all we have to do to solve this problem. There's nothing else involved there. So you had the right instinct that we were going to have to multiply in this case, but that's solving the problem itself. That's not like a preparation for solving the problem. Okay, so I think you came up with the right answer. So the one thing that was leading you a little bit astray is for a second there, you weren't quite using the method. You were asking, gee, do I need to prepare this in some way before I can use the method? But the method is the preparation, so to speak. All these problems are basically the same. All these problems are the same. You write the target units, you write the starting information, and then you write down the conversion ratio so that you can figure out how to convert from one unit into another. And then the process of writing down those units tells you whether you should be multiplying or dividing. So the important thing is to see how all these problems are the same. Now, I suppose eventually, as we get to harder and harder problems, maybe eventually we'll get to more weird problems where you can't just stick to the systematic method. But we're not ready for that yet. So far we're just doing problems that you can do with this systematic method. And that would account for the vast majority of the problems you're likely to see on the test anyway. Okay, so anyway, we went through this and we got the right answer here. You could have gotten a prediction before you started. You could have said to yourself, well, I know that I have, so are we starting with more or less than a mole?
More.
So we know from the start that our answer is going to be bigger than 6 times 10 to the 23, right?
Yeah.
We could have predicted that from the start. We could have predicted our answer will be more than 6 times 10 to the 23 molecules. It's not a bad idea to try to get into the habit of making those predictions. That way you can make sure your answer is making sense, and that way you have a little bit more intuition for what you're doing. Now, one thing you did that was really good on this problem is that you weren't on autopilot. If you had been on autopilot, you would have used this conversion ratio with the 1 mole on the top and the Avogadro's number on the bottom, just because that's what we did on the two previous problems. The two previous problems, the ratio looked like it had the 6 times 10 to the 23rd on the bottom. So it's good that you realized from the units that here we had to write it the opposite way. So we just have to be awake and alert for each problem. So that was correct. Okay, so I think that was making sense. So let's summarize here. Let's go back to our conversion table. So now we've learned a new type of conversion. We learned before how to go from grams of X to moles of X. What's the new type of conversion we've learned how to do? We've learned to go between what and what?
Moles of X to molecules of X.
That's right. Or I'll just write it as X to moles of X. I'm not going to write the word molecules here. You can read this as individual X's to moles of X, because these don't have to be molecules. They could be atoms or they could be ions, depending on the problem. So we'll just say you can go from individual X's to moles of X. So this is the best way to write it out. And then what is the conversion ratio? What is the conversion ratio between X and moles of X?
It has to do with Avogadro's number.
Yeah.
Either 1 over or...
So let's write it down specifically. What should I write down specifically as the two possible conversion ratios here for our reference?
1 over 6.02, or 6.02 times 10 to the 23rd. Or 6.02 times 10 to the 23rd over 1 mole.
Yeah, these conversion ratios aren't useful unless we put in units. So let's go back and fill in the units. What are the units that should go up top here?
Mole.
Mole of what? Mole of X in our little table. So this would
Moles of
be
X.
1 mole of X. And what do I write as the substance or the units down here?
Just molecules, I guess, or individual.
I would just write X. You could read that as individual X's, but for our reference, I'll just write that as X. That matches what we've been writing in our previous problems, right? We've been writing things like 1 mole of CO2 over 6 times 10 to the 23rd plain old CO2. That's the right way to write it down. What we want to have here is a reference table so you know what to write down for solving problems. So then what units should I write up here?
Just X again.
Yeah, which we would interpret as individual X's. And what do I write down here?
Moles of X.
Good. Now you just have to remember that when you're actually doing an individual problem, you're not really going to literally write X, you'll write the appropriate substance. For example, if you were going between water and moles of water, you would have 6.02 times 10 to the 23rd water over 1 mole of water. This is just for reference. All right, so now we have 2 different types of problems that we can solve in this conversion table. So as you go through your chemistry course, you're just going to keep adding more and more entries into this conversion table, more and more different types of units that you can convert between. So now we have 2 of them so far. Good. So notice that most conversion ratios don't come from the periodic table. This is one that doesn't come from the table. All right, good. I didn't really explain what a mole is. Why is it convenient to define a mole as 6.02 times 10 to the 23rd? Why is it convenient to use such a huge number in chemistry? Why is it convenient to work with such a huge number? Well, the reason is if you have an ordinary sized amount of a substance, the number of molecules will always be huge. If you have an ordinary sized amount of a substance, say 2 grams or 3 grams or 10 grams, the number of molecules is always going to be huge because remember the molecules are teensy tiny. Because the molecules are so small, there's always going to be a huge number of them. It's just like suppose that you scoop up, you fill a bucket with sand. The number of grains of sand in your bucket is always going to be huge because the grains of sand are so small. The number of grains of sand on the beach is huge because the individual grains are so small, but the number of molecules on the beach is even way more huger than that. So that's why it's convenient to work with such a big number because there's so many molecules in any ordinary sized amount of substance. We know from the periodic table that if you had, let's say that you have 12 grams of carbon. If you have 12 grams of carbon atoms, how many moles is that? We know that's 1 mole of carbon, right? You can see from the periodic table that there's 12 grams per mole. But remember that what that really means is that how many individual carbon atoms does it take to make up 12 grams? How many individual carbon atoms would it take to have 12 grams?
6.02 times 10 to the 23rd.
That's right. It would take a huge number. Why does it take so many atoms just to make a measly 12 grams? Because the carbon atoms are so small. That's the motivation behind the number mole. It's convenient to use a huge number in chemistry because anytime you have 12 grams or 14 grams or any ordinary number of grams of a substance, you're going to have a huge number of individual molecules or atoms. So it's easier to keep track of that if we use a number for such that huge number. By the way, that would be really the definition or a definition of a mole. Another definition of a mole is the number of carbon atoms in 12 grams of carbon. I think that's pretty close to the official definition of a mole. The official definition is that a mole is the number of carbon atoms in 12 grams of carbon. But like I said, that's not I wouldn't emphasize that too much because that's not what's important for you for solving problems. What's important for you for solving problems are these 2 conversion ratios. So these are the real definitions of a mole that are useful for us for solving problems. Okay, so let's move on to some harder problems here. Let's say we've got this. Let's say we've got 50 grams of methane is how many molecules of methane? Now, I'll warn you, this problem is a little harder than any of the problems I gave you before. This is a little harder than the previous problems. But I want you to take a shot. Take a shot at trying to solve this problem on your own. Tell me what you'll write down. But if you get stuck, I'll give you some help. So give this a shot.
Okay, so the first thing you do, I think, is convert the grams to moles. So you do first write down your target unit, which would be moles of methane. Then you write down what you have, which is 50 grams of methane. And the number, it's going to be 12, and so it's going to be 16 grams for every mole of methane. So you write 1 mole on top, 1 mole of methane, or 16 grams methane, which would give you 3.1 moles. And then you would take that 3.1 moles of methane times Avogadro's number over 1 mole of methane, which gives you 1.8 times 10 to the 24th.
Let's see. On my calculator, that would round to 1.9 times 10 to the 24.
Oh, yeah.
Individual molecules of methane. Okay, well, that's good. That was a harder problem than the ones we did before, but you figured out a method and you got the right answer. So that's a good adaptation to that problem. All that I'm going to do now is show you a way that's a little more systematic and efficient as the problems get harder. So what you did is you said, this is a harder problem, so you broke this up into 2 easier problems. You basically broke this into 2 unit conversions. That's a good idea. That worked perfectly fine. However, it's actually better in chemistry to do unit conversions in 1 step rather than in 2 steps. So what we do is, let's just say that the target units are molecules of methane. Those are the target. And let's see how we would do this in 1 step. So to do this in 1 step, you write both conversion ratios from the start before you do any calculations. As it turns out, this is the standard method in chemistry that we want to learn. Because eventually you're going to get to problems where you're doing maybe 5 or 6 conversions on the same problem. And if you broke it up into 5 or 6 separate conversions, it's too much work. It's better to put them all in 1 step. So how would we do this? Well, you would say to yourself, here's the first step, and I can see that the grams are going to cancel, and then I can see if I only used this conversion ratio, I would have moles of CH4. But I know that's not what I want. What I want is individual molecules, so I know that then I'm going to need another conversion ratio. I'm going to need moles of CH4 over individual CH4, and I can write that conversion ratio here. Okay, good. And now I can cancel diagonally again. Now the moles of CH4 will cancel with the moles of CH4. And now I can see I'm done, because now the only units that are left standing are the individual CH4s. And only now that I can see that I've canceled all the units except the units that I don't want, now I'm going to go back and do all the calculations in one fell swoop. So that would be 50 times 1 divided by 16 times 6.02 times 10 to the 23rd divided by 1. Or you can just leave out the ones. You can just say it's 50 divided by 16 times 6.02 times 10 to the 23rd. You can just leave out the ones because multiplying or dividing by 1 doesn't do anything. So this would mean divided by 16, and this would be multiplied by 6.02 times 10 to the 23rd. And obviously you would get the same answer you got anyway, let me check that. Times 16 times 6.02 times 10 to the 23rd, 1.9 times 10 to the 24th. Okay, good. So then we would do that, and now we're done. So the way you did wasn't wrong. Obviously, you got the right answer. But as we go to harder and harder problems, it gets unwieldy. So we want to start learning how to do it in one step, like this. But that's good that you worked that out. So now we're starting to move on to harder problems where you have to use more than one ratio in the problem. And it becomes more and more important to keep canceling the units as you go. Again, you were mentioning at the start that what gave you trouble was setting up the math. And what we're seeing is the units tell you how to set up the math. If the units are canceling, then you set up the math correctly. And if the units are not canceling, then we haven't set up the math correctly yet. Okay, so anyway, you ended up with this answer. By the way, we should ask, does this answer make sense? Does it make sense that we would get such a super huge number? Does it make sense that we'd get such a super huge number? Yes, because remember, now we're counting individual molecules. Well, we know that when we have any ordinary number of grams, there's automatically going to be a huge number of molecules. Just like if you have a bucket of sand, that already has a huge number of grains of sand inside of it. So we could have predicted from the start that the answer would be a huge number, even though we couldn't predict what it is exactly. Okay, so you should have this example in your notes. You can go back and try this again, but that's good that you worked out the right answer on your own. So let's see. So suppose now that we've got 100 grams of ammonia is how many molecules of ammonia. All right, so let's try this. So again, try using the systematic method we were just talking about in the last problem and tell me what you're writing down.
Okay. First, you write down your target value, which is just going to be individual ammonia. And then you write down what you have, which is 100 grams of ammonia. So then first you'd write down your mole conversion ratio, which is going to be 1 mole of ammonia for every 23, 14, 17 grams of ammonia. And then you do the same thing, but you do Avogadro's number on top, which would be 6.02 times 10 to the 23rd NH3 over 1 mole of NH3. So then the grams cancel and the moles cancel. And then what you would do then I got 3.5 times 10 to the 24th.
Okay, good. That's a huge number. Why does it make sense to get such a huge number as our answer?
Because you have many more grams than is in 1 mole of ammonia.
Let's see, I don't think that quite explains it, really. Because you were just saying, you were kind of relating grams to moles. The reason is because in any ordinary number of grams, there will be a huge number of individual molecules. So the reason we have such a huge number of individual molecules is because each of them is so tiny. It's not really related too much directly, but to grams to mole. I don't know, maybe you were thinking the right thing. Okay, so anyway, that's the right way to set this up. You set this up correctly, and it's good that you were careful to cancel the units and write down all the substances. So that's good. There's something I want to kind of clarify here. So you were using the conversion ratio here of, say, 17 grams ammonia to 1 mole of ammonia. How do you interpret this conversion ratio? What this tells us is if we had 1 mole of ammonia, we would have 17 grams of ammonia. Or if we had 17 grams of ammonia, we would have 1 mole of ammonia. That might seem obvious, but the key word there is the word if. Something that you have to realize in chemistry is that there's two different types of numbers in each problem. In each problem, there's two different types of numbers. Some of the numbers are actual, and some are hypothetical. Some of the numbers are actual, and some are hypothetical. The numbers on the top and the bottom of ratios are generally hypothetical. The numbers on the top and the bottom of ratios are hypothetical, and the numbers that are not in the ratios are actual. So here's what I mean by that. In this problem, do we really have 17 grams of ammonia? Well, no, that's just hypothetical. What we really have is 100 grams, right? That might seem obvious, but I notice that students oftentimes start to get confused about that. When we write this down, it doesn't mean that we actually have 17 grams. This is the actual number. This is the number we actually have. This is just hypothetical. This is how many grams we would have if we had 1 mole of ammonia. So it's important to realize that to avoid mistakes. Just because you wrote down a number doesn't mean it represents what you actually have. If it's inside of a ratio, it represents a hypothetical quantity. Same deal. Here we wrote 6.02 times 10 to the 23rd individual ammonias. 6.02 times 10 to the 23rd individual ammonias. Does that mean that we really had 6.02 times 10 to the 23rd individual ammonias in this problem? Did we really have 6 times 10 to the 23rd individual ammonias in this problem?
No.
No. How many did we really have? How many individual ammonias did we really have?
3.5 times 10 to the 24th.
Yeah, that's what we figured out. So this number is the actual number. You can see that because it's not inside of a ratio. This is not inside of a ratio. And this number here is just hypothetical. This is how many ammonias you would hypothetically have if you had 1 mole. If we had 1 mole, we would have this many ammonia. So it's important to realize that some numbers are hypothetical, some numbers are actual. How do you tell the difference? If the number is inside of a ratio, it's usually hypothetical. And if it's outside the ratio, it's usually actual. Those are terms probably that your instructor is not going to use. Your instructor is probably not going to call things hypothetical and actual, but that's because it's already obvious to your instructor. Students oftentimes confuse those, so I think it's important for a student to use those ideas so they don't confuse those things. Okay, maybe we'll come back to that if we have any trouble with that, but let me give you another problem. So let's see. Let's start this last problem. Good. So let's say we have eight times 10 to the 23rd. What do I want? F2 molecules is how many grams? So try working this problem out on paper.
Okay. First, you write down your target value, which is grams of F2. Then what you would do is you write down what you have, which is 8 times 10 to the 23rd. Then you need to convert that to moles, which would be times 1 mole of F2 divided by 6.02 times 10 to the 23rd with individual F2. Then you would multiply that number by, let's see, the grams. So you do 1, no, not 1. 1. How many grams of F2? 110. 110 over grams of F2 over the 1 mole F2. Okay, so I got 1.33 moles. Then we need to convert that to grams. So we just multiply that by 110, which is 146.3 grams.
Okay. So let's see. You were using the systematic method. What units did you write here?
Where? Oh, just individual F2.
Good. And then you can see that.
Oh, I used the wrong mass.
Yeah.
Wow.
Okay, so let's go back and fix that.
Okay, so it shouldn't be 110. It should be 38. Okay. I used the mass of iron instead of fluorine.
Oh, I see. I was wondering how that came up. All right, that's good to know how that came in. Okay.
Okay, so I got 50.5 grams.
Okay. Well, that was a good systematic approach. You were putting in the units. So I was trying to trap you or trip you up here because the problem here, did you see, is kind of the reverse of the earlier problems. The earlier problems, I was giving you the individuals and asking you for molecules, and here I'm asking for molecules and no, I'm starting with individuals and going to grams. Well, yeah, anyway, it's the reverse. It's the reverse order. But that didn't give you any trouble because the point is we're not supposed to be on autopilot. Every problem we just start from scratch, and we figure out what calculations we have to do just by focusing on the units. So it didn't really seem to phase you that reversed. So that's good. And again, that you caught your mistake of using the wrong mass here. And that again is why I said it's just important after today to go back and redo all these problems again, and hopefully you've got a bunch of homework problems like these to try as well. Because you have to get to the point where you can do these automatically and quickly without any careless mistakes so that you can do them under time pressure when you're taking the real test. A lot of the time, these will just be part of a harder problem. We're still building up to harder and harder problems, so we have to get to the point where these we can get right with no careless mistakes. I think we're already making pretty good progress, so you caught that mistake. Now, one thing that you should notice here is, how is it that we could start with such a huge number and then end up with an ordinary size number? Does that make sense? Is this a reasonable answer? Why could we start with such a huge number and get an ordinary size number? Well, it does make sense because remember, because molecules are so small, it takes a huge number of molecules just to have an ordinary size number of grams. So you should always ask yourself whether the answer makes sense, but this one does. Okay, good. So that ended up being the right answer. Okay. Well, you made that one careless mistake here, but I think you're understanding this process, so we can go on to another problem. So anyway, I don't need to add another conversion ratio, because those new problems, we didn't need any new conversion ratios, but now we've learned how you can use multiple conversion ratios in the same problem. Notice why do these two link up? Because they both have moles of X. Both of these have moles of X, so you could start here and convert to here, and then convert into grams. Or you could start with grams and convert into moles and then convert into X's. And as we add more and more layers to this table, there will be more and more conversions that we can do. Oh, there was one thing I wanted to mention on the last problem. I'm not sure, but it sounded like at first you were just doing the first multiplication and figuring out the number of moles, and then doing another multiplication to figure out the number of grams. Now, there's nothing wrong with that theoretically, but as a matter of practice, we should just get into the habit of doing all the calculations in one fell swoop. It's a good habit to get into the calculations all in one swoop. You can do this in one step on your calculator. 8 times 10 to the 23rd divided by 6.02 times 10 to the 23rd times 38 grams. You can do that in one step on your calculator and get the right answer. There's nothing wrong with doing in separate steps, but as the problems get more and more complicated, it's good to just do it in one step. Okay, so let's keep going. All right.
Well, I would do it like that, but I forgot my calculator at school, and I have to do all these on my phone.
Oh, I see. Okay.
So,
all right. I see. All right. Yeah. So now I understand. Okay, yeah. If we have another session, it's always good to use the same calculator you're using in class. All right.
Okay.
So, and well, actually, to be more specific, you should be using the same calculator you're going to use on the actual AP test, because there are some tricks that you have to learn how to use your calculator on some of these types of problems. So you should figure out now which calculator you're going to use on the actual AP test, and that's the best thing to use in the tutoring session, so we can work out any bugs that might come up there. Okay, but we're fine for today. So let's see. Next type of problem. Now we need to start talking about chemical equations. So let's look at, say, this equation. All right. Have you guys started working with these types of chemical equations in class?
Yeah.
Yeah, okay. This is pretty standard. Have you ever seen these types of symbols? Do you know what this stands for?
Yeah, it means they're gases.
Okay, very good. Yeah, so that tells us the phase. So what are the units on this number 2? And by the way, we might say, so this number here is what's called a stoichiometric coefficient. This number is what's called a stoichiometric coefficient. So the stoichiometric coefficient here is 2. The stoichiometric coefficient here is 2. I didn't write a number here. Do you know what's the stoichiometric coefficient if I didn't write a number?
1.
Yeah, so you can write a number 1. What are the units on these stoichiometric coefficients? This means 2 whats?
Moles.
That is usually the most convenient units. So this would be interpreted as 2 moles of H2 plus 1 mole of O2 gives 2 moles of H2O. So actually, I guess the answer you gave wasn't quite complete. Since I was asking you for the units on this number, I guess what you should have said was 2 moles of H2. And then the units on this number would be 1 mole of O2. And then the units on this number would be 2 moles of H2O, because we've seen on the previous problems it's important not just to write the bare units, but also the substance. Now, this is a little tricky because there's other possible interpretations that are also correct. Besides interpreting these as moles, you could also interpret them as individuals. You could say also that 2 individual H2 molecules plus 1 individual O2 molecule forms 2 individual H2O molecules. That's also an acceptable interpretation. Because if you have equal numbers of moles, you would automatically have equal numbers of molecules. So if the equation works for moles, it would also work for molecules. And sometimes there's some other interpretations you can use as well. But when you're doing chemistry, usually the right interpretation is moles. So that's the one that we'll be focusing on here. Now, one thing that's really important to realize, remember that we were talking about how some numbers in chemistry are actual and some are hypothetical. Are these numbers actual or hypothetical? And the answer is these are hypothetical. This means if you started with 2 moles of H2O and if you started with 1 mole of O2, then you would hypothetically produce 2 moles of H2O. It doesn't mean that you actually have 2 moles or that you actually have 1 mole of O2. It's just hypothetical. For example, it's possible that you really have 2 moles of H2. Twice as many as it says here. How many moles of oxygen do you think you would need to react with that? If you have 4 moles of H2, how many moles of oxygen do you think you would need to react with that?
2 moles.
Twice as much as before. Good. And then how many moles of water do you think you would get?
4.
Good. Well, that really shows how the original numbers were just hypothetical. Here's another set of hypothetical numbers. If you have 4 moles of H2, then you would react that with hypothetically 2 moles of O2 to hypothetically get 4 moles of H2O. Or let's just do one more example. Let's say that you started with 6 moles of H2. How many moles of oxygen do you need to react that with?
3.
3 times as much, because this is 3 times as much. And that would produce how much water?
6. 6 moles.
Yeah. So notice there's more than one way to write a balanced equation. These are all balanced equations. Probably this way is the best because the numbers are reduced. Usually you want to use the numbers reduced to the smallest possible integers. So these are all correct, but this would be probably the best and most convenient. But anyway, hopefully that makes it clear why these numbers are just hypothetical. So let's erase that. I said before that usually numbers that are not in a ratio are actual, but I guess this kind of is an exception to that. These numbers are not in a ratio here, but they're still just hypothetical. So here I have this equation. Well, let me give you another equation that N2 plus H2 forms NH3. And to balance that equation, I guess I would say 2N2 and 3 of these. All right. So here's a trick question. The question is, how many moles of H2 are we starting with? The question is, how many moles of H2 are we starting with in this example?
6.
Oh, let's see. That wasn't the answer I was expecting. Maybe you multiplied 3 times 2? All right.
Yeah.
Now, that was a trick question. The right answer is we can't tell. Because remember, the stoichiometric coefficients are just hypothetical.
Yeah.
Sorry, that's kind of a mean trick question. But the point is, the equation doesn't tell you the actual amounts that you're starting with. The equation doesn't tell you the actual amounts you're starting with. It's just hypothetical. It tells us that hypothetically, if we started with 1 mole of N2, then we would need hypothetically 3 moles of H2. But how much H2 do we actually have? Well, we don't know. I mean, how much H2 do you actually have? You actually have 0 moles of H2, right? I'm pretty sure you don't have any H2 in your pocket right now. So, this shows us that even though we're looking at this equation, it's just hypothetical. It doesn't tell you how much H2 you really have. The amount you have could be any number, including 0. Okay, so these numbers are just hypothetical. So going back to this equation, in this equation, if we're using this equation, how much H2 gas are we actually starting with?
We don't know.
Yeah, trick question, we don't know. We only know that hypothetically it would take 2 moles to react with 1 mole of O2. Okay, maybe as we go on, you'll see why I think that's important. Let's see. Are we ready to start with some problems here? I guess so. Now, this is called a balanced equation. Have you learned how to balance equations in your course?
Yeah.
Yeah. Why do I say this is balanced? How would you check that this is balanced?
Well, you'd have to see if all of the values on each side were all balanced.
Yeah, so check that. How would you check that?
Well, I'd look on the left, see there's 4 hydrogens. Look on the right, there's also 4 hydrogens. Look on the left, see there's 2 oxygens. Look on the right, there's also 2 oxygens.
Yeah, because if 2 times 2 is 4 hydrogens, 2 times 2 is 4 hydrogens, 1 times 2 is 2 oxygens, 2 times 1 is 2 oxygens. Good. So we need a balanced equation here in order to do stoichiometry. So now that we have this balanced equation, the thing that's important to realize is this gives us a bunch of new conversion ratios. Remember, that's what our quest is. We're questing for new conversion ratios. Remember, what are the units on this number 2?
2 moles.
2 moles of what?
Of H2.
So here, and what are the units on this number?
1 mole of O2.
So here's one of the conversion ratios that we can get from this equation. We can get this conversion ratio from this equation. And then obviously another conversion ratio we could get is 1 mole of O2 over 2 moles of H2. Now, I think there's a bunch more conversion ratios we can get as well, so let's practice with that. Another conversion ratio we could get is 2 moles of H2 over 2 moles of H2O.
Okay, yeah.
I could take this substance, and I could write this conversion ratio. I could reduce this now to 1 to 1, but to make it clear what we're doing, I'm not going to reduce it. Actually, when you're doing stoichiometry, you usually don't reduce the ratios. So I'm not going to reduce this. I'll just leave this as 2 over 2. And clearly this gives us another conversion ratio, which is 2 moles of H2O over 2 moles of H2. So there's another conversion that we have. All right, good. So I think there's another set of conversion ratios we can get from this equation. What would you say is another conversion ratio we could get from this equation?
1 mole of oxygen gives us 2 moles of H2O. And then vice versa.
Right. 2 moles of H2O over 1 mole. And I think that's it. I don't think there's any more conversion ratios we could get. Now, on any particular problem, obviously you wouldn't write down all 6 of these. On any particular problem, you only write down the ones that you need to solve the problem. But to get started here, it's good to write, as a practice, to write down all the possible conversion ratios that we could get. By the way, remember I was saying a second ago that these numbers are only hypothetical, not actual, and now you can see why, because they're really parts of conversion ratios. We already saw before that if a number is on the top or the bottom of a ratio, it's hypothetical, not actual. So now that gives us a better way to interpret all these numbers. Okay, so those are all the conversion ratios we could get from that equation. So let's say we had this equation, N2 gas plus H2 gas forms NH3 gas. And let's try to write down all the conversion ratios that we could get from this. Well, we can't do anything until we've balanced the equation. It's only the balanced equation that gives us the conversion ratios. Do you know how to balance equation? Try balancing this equation. What would you get?
You get 1 mole of N2 plus 3 moles of hydrogen, or yeah, 3 moles, but it goes to 2 NH3.
Yeah, all right, that looks right. You can see that, for example, there's 6 hydrogens now on the left and 6 on the right. So it looks like you balanced that correctly. All right, and now we can write the conversion ratios. So for practice, let's do that. Let's write down all the conversion ratios. Let's just write them out. So what are the conversion ratios we could get?
1 mole of N2 gives us 3 moles, 2 NH, no, sorry. It gives us 2 moles of NH3. Yeah, 2 moles.
1 mole N2 over 2 moles of NH3. Good.
Yeah. And vice versa. 2 moles NH3 gives us 1 mole N2. 3 moles of H2 gives us 2 moles and H3. Let's see what else. Oh, and then vice versa, that 2 moles NH3, 3 moles of H2. Then there's 1 mole of N2, 3 moles of H2, and vice versa of that.
Okay, good. That was good. Like I said, from now on, we'll never have to write down every single conversion ratio again. On any problem, we only need 1 or 2 of these. But it was good practice just to see all the conversion ratios we could get. But notice, none of this would make sense if we hadn't balanced the equation first. So you need to use the balanced equation to get the conversion ratios. One thing that you can see here is notice it doesn't really matter that much whether you're using one starting, have you heard the term starting materials and products? I guess you've heard those. So
Yeah.
the things on the left are the starting materials, the thing on the right is the product. But notice that as far as conversion ratios are concerned, it doesn't really matter very much whether you're using 2 starting materials or a starting material and a product or 2 products. You write the conversion ratios the same way. For example, here you had 1 starting material and 1 product. And here you had 1 starting material and 1 product. But for this ratio, you had 1 starting material and the other starting material. But that didn't really change how you wrote the ratios. It would change how you interpret them a little bit. How would you interpret this? You would say, if I use 1 mole of nitrogen, N2, that will produce 2 moles of NH3. Or if I want to produce 2 moles of NH3, I need to put in 1 mole of nitrogen. Or if I put in 3 moles of hydrogen, that'll produce 2 moles of NH3. These ratios have 2 starting materials, so you would interpret them a little bit differently. Here you would say, if I want to react 1 mole of nitrogen, then I'll need 3 moles of hydrogen. Or if I want to react 3 moles of H2, I'll need to react that with 1 mole of N2. So you would interpret it a little differently, but it doesn't really change how you would figure it out. Okay, so I think we're already ready to go back to our table and write down another type of conversion ratio. So can you see, what have we learned to convert between? Remember, before we learned how to go from grams of X to moles of X, or individual X to moles of X. This might be a little hard to put into words, but what should I write here and here? What have we learned to
Would
convert
it be the
between?
moles of one of the parts of a reaction and the moles of another part?
Excellent. Yes, that's exactly right. So if we want to be algebraic about it, like mathematicians, we could say we're converting from moles of X to moles of Y. That's our new conversion. Moles of X to moles of Y. Now, obviously, on any individual problem, you're not going to use the words X and Y. You'll use the individual substances, like moles of N2 to moles of NH3. So these are just placeholders. Do you see how this conversion ratio then is much more exciting than the previous conversion ratios? What's so great about this? This is the first conversion ratio that goes from one substance to a different substance. All the earlier conversion ratios were just telling you two things about the same substance, two things about the same substance. But now, if we know something about one substance, we can learn something about another substance, which is really what chemistry is about. It's about putting in some substances and getting out other substances. So this is, in a way, a more interesting conversion ratio. So where do these conversion ratios come from? We have to write above the arrow where they come from. These conversion ratios
balanced
come...
equation.
Yes, they come from the stoichiometric coefficients of the balanced equation. So what I should write down here is the conversion ratios come from the stoichiometric coefficients of the balanced chemical equation. So you have to balance the equation first before you can use this. All right, so now we have three types of things there. Let's go on then to this. All right, so let's see. Where was I? Let's say we've got all right, first, see if you can balance this equation.
Okay. Okay, I got it, I think.
Okay, good. So what are the
You have 1
coefficients?
mole methane plus 2 moles of oxygen goes to 1 mole of carbon dioxide plus 2 moles of water.
So there's 4O2 on the left, 4 on the right. Okay, good. Looks like you're not having any trouble with that. What does this symbol stand for?
Liquid.
Okay, so now let's say okay. Well, we haven't ever done a question quite like this before, but maybe you can figure out how to apply our previous methods to this. So try working this out on paper.
Okay. First, I guess you put your target unit, which is going to be moles of H2O. And you write what you have, which is 2.7 moles of methane. Then you plug in your conversion units, which would be there's 2 moles of water for every 1 mole of methane, which would give you 5.4 moles of water.
Okay. That doesn't seem to give you any trouble at all. Okay, excellent. So like I said, notice we've never done a problem quite like this before. But you were still able to figure out how to do it without much problem because you're seeing that all these problems are the same. All these stoichiometry problems are just unit conversions. So once you learn the method for unit conversions, you can really adapt that to any type of problem. Again, what you were saying at the beginning was that you were having trouble setting up the problems. But now we're seeing the way to set it up is by using the units. The units tell you how to set things up so that you know what to do. The biggest mistake people would make here is when people try to do this in their head or unsystematically, a lot of the time they multiply when they should divide, or they should divide when they should multiply. Maybe some people would do 2.7 divided by 2. But if we're systematic with the units like this, then we can know with confidence whether we should be multiplying or dividing. Okay, all right, so that's good. You worked out how to do that. So by the way, you can see here the difference between actual numbers and hypothetical numbers. So for example, here you were using this number 2 moles of H2O. Is this actual or hypothetical?
Hypothetical.
Because how many moles of H2O did we really produce? How many moles of H2O did we really produce?
We don't know.
You were saying that this is only the hypothetical number of moles. How many moles of H2O did we really have in this problem?
5.4.
That's what we figured out. So again, hopefully that makes it clearer that there's a difference between hypothetical and actual. We would have produced 2 moles of H2O if we had hypothetically started with 1 mole of CH4. But actually, we didn't start with 1 mole of CH4, we started with 2.7 moles. So that makes it clear why we really need to use these ideas of actual and hypothetical and not get those confused with each other. Okay, well, it looks like you definitely worked that out. Let's ask you this. How many moles of O2 are needed to produce 5.2 moles of CO2. Let's try working this out on paper.
Okay. Alright, so first thing, you write down your target unit, which is moles CO2, and you write down what you have, which is 5.2 moles. No, sorry, target unit is moles of oxygen. Moles of O2. And then you write down what you have, and write down your conversion ratio, which would be there is 2 moles of O2 for every 1 mole of CO2. Okay, then those cancel. Then you get 10.4 moles of O2.
So what units did you write here?
CO2.
Okay, good. And again, we should always physically slash these out to make sure we're doing the units correctly. Okay, excellent. So this problem was pretty similar to the one before. Do you see how this is conceptually different? The first problem is kind of more natural because I gave you an amount of starting material and asked you how much product you could get from it. And this problem might feel a little weirder. This problem might feel a little bit more backwards because in this problem, I gave you the amount of product and I asked you to work backwards, so to speak, to the amount of starting material. That might possibly be why originally you wrote down the wrong target units. It might be that you wrote down the wrong target units because you were confused between the starting materials and the product. So notice, just because something is the product doesn't mean it's the target units. The target units are not what we're trying to make. The target units are the unknown. So if the starting material is the unknown, then that's the target. It's not always the starting material. So conceptually here, this might seem more complicated because we're having to work backwards from 5.2 moles of this to an unknown amount of this. But the nice thing about this unit conversion approach is that it really wasn't any more difficult mathematically. In fact, you hardly even have to think about the fact that you're going backwards. If you just do this systematically, it just works out just as nicely. So the lesson here that we're trying to learn is you can use this to figure out an unknown amount of product from a given amount of starting materials. Or just as easily, you can figure out an unknown amount of starting material from a known amount of product. And another type of problem that you could do is if you were given an amount of starting material, you could figure out the unknown amount of the other starting material. You could move between two starting materials. Or another thing you could do is if you were given a certain amount of product, you could figure out the unknown amount of the other product. I don't think I'm actually going to give you those questions right now because they're all done the same way. I think you're already seeing how to do those. But the point is you can do a whole bunch of different types of problems here. So again, it really doesn't matter very much whether you're dealing with starting materials or products for these types of problems. The unit conversion technique is the same. But I think you're getting the hang of that already. So let's just keep making this more complicated. Whoops. All right, so let me give you a harder problem. But I think I'll stick.
Do you think before we call this off, we could do a limiting reaction problem?
Hopefully, we're building up to that basically.
Okay.
So we'll see whether we have enough time to get to that. We're nearing in on it. Okay. So let's see what we're doing here. So what we're doing here is necessary building blocks for limiting reagent.
Okay.
Okay, let's try this.
Okay, so first we need to write down target units, which is grams CO2. Write down what we have, which is 60 grams of O2. Then we write down our inversion ratio. Let's see. There is 1 mole of CO2 for every 2 moles of O2, which means that we will get 30 grams of CO2.
Now let's see. Let's look at that conversion here. Did you use a slash mark to show the units that you're canceling?
Oh, no, I did not.
Okay.
Wow. Okay. So this is a little bit more complicated than I thought.
Yeah.
Okay, so start over then 60 grams of O2. So we're going to have to change that to moles first. So there's 1 mole of O2 for every 32 grams, which is 1.7. And from there we go grams of O2 times grams of CO2. Okay, how would you write this one all in one equation?
Okay, yeah, so let's talk about this together a little bit. So first of all, let's look at the first units you wrote down. Your first attempt, how do we know that this first attempt doesn't work? Because the units don't cancel. We can see this first attempt doesn't work because these units would not cancel with these. So this looks better. So now did you use the slash mark to show the units that canceled?
Yeah.
So after you cancel those units, what units do you have left?
Moles of oxygen.
So are we done? No, because that doesn't match the target units yet. That's why we have to write the target units first to see when we're done. So we need to do another conversion ratio. Now, it should be obvious what units go down here. What units do
Moles of oxygen.
Right. That should be obvious because we need that to cancel. And then what units do we put up here? Well, we have to put some units that will help us to get to the target, but they also have to be units where we know the conversion ratio. So what do you think? What units could we put up here?
Moles of CO2.
That's right. That turns out to be the convenient thing. That's progress because that gets us towards CO2. So what would be the numbers?
1/2.
1/2. All right, very good.
And then you have, sorry.
No, go ahead.
Then you would have to multiply by 44 grams of CO2 over 1 mole of CO2. Okay, let's see. This will be 60 divided by 32. 44. I got 41.25 grams.
Okay. So this is the hardest problem that we've done so far, but this is the only, probably the first problem that was as hard as you might see on the test, or close anyway. All right, so notice here, yeah, so here's the correct method. So here we have a whole bunch of conversion ratios in a row, and the key here is just keep slashing out the units that have canceled. The grams cancels, which leaves you with moles. Then the moles cancel, we had moles of O2, then we cancel the moles of O2 to get moles of CO2, and then we canceled that to get grams of CO2, and then we know we're done because that's the target units. That's why I've been encouraging you to always write the target units first, because otherwise you don't know what conversion ratios you need. This is a little bit like a puzzle. You're trying to kind of feel your way through the dark from the starting material to the product. Sometimes it's not really obvious what the right conversion ratios are. Sometimes you just have to do trial and error. Sometimes you just have to do trial and error until you get a string of conversion ratios that give you the right answer. So if you're not sure what to do, you just have to try something, writing it down, and see if that will work. The key step is this one when we moved between two different substances. We moved between O2 and CO2. So notice we only have one way to go from one substance to another. Anytime you're going to go from one substance to another, you have to be dealing with moles. If you're going to go from one substance to a different one, you have to be dealing with moles. So since the problem gave us grams, we had to first get into moles. Then we could go from one substance to another, and then we could actually answer the question, which was also about grams. Okay, so this is a pretty typical type of stoichiometry problem. Now, you had a little trouble with this, but there's one trap that you avoided that was good. Remember we said, what are the units on this number? Well, this could be interpreted as 1 mole of CH4. Remember I said it could also be interpreted as 1 molecule of CH4. But I think something you've already figured out is, could these be interpreted as grams? Could we say 1 gram of CH4 plus 2 grams of O2 gives 1 gram of CO2 and 2 grams of H2O?
Yeah.
Actually, that would be the trap. If you could have done that, you could have done this problem much more quickly. If you could have done that, you could have just done it all in one swoop. These are not grams. So that's an important thing to realize. These numbers, the stoichiometric coefficients could be moles or individuals, but they can never be grams. And the reason is, suppose that you have equal numbers of moles of two substances. Let's say you have 3 moles of CH4. And, well, let's just make it simple. Let's say you have 1 mole of CH4 and you have 1 mole of O2. If you have equal numbers of moles, does that mean that you have the same number of molecules of both of these things?
No.
Think about that a little bit more. If we have 1 mole of CH4, yeah, and 1
yes,
mole of,
you do.
in fact, how many molecules do we have? If we have 1 mole of CH4, how many molecules of CH4 do we have?
6.02 times 10 to the 23rd.
And how many molecules of O2 would we have?
Same.
That's right. So that's the reason.
6.02 times 10 to the 23rd.
That's the reason why these could be interpreted as either moles or molecules. Because if you have equal moles, you have equal molecules. But does that also mean that we have equal numbers of grams of both of these? If you have 1 mole of CH4, does that mean you and 1 mole of O2, does that mean you have equal number of grams? We saw that if you have equal numbers of moles, you also have equal numbers of molecules. If I have 1 mole of CH4 and 1 mole of O2, does that mean I have the same number of grams of CH4? And no. In fact, how many grams of CH4 would this be?
16.
This would be, from the periodic table, this would be 16 grams of CH4, but how many grams of O2 would it be?
32.
That is the reason why, that's the reason why you can't say that moles are kind of equivalent to grams in this equation. Just because it takes twice as many moles of O2 as CH4 doesn't mean it takes twice as many grams, because they have different molecular masses. Okay, actually, I kind of messed you up there because you were kind of seeing that when you started. When you started, you weren't using this for grams, and I kind of tried to tempt you to do that. But anyway, that's a good thing to watch out for in the future. These numbers can be interpreted as moles, or sometimes they could be interpreted as individual molecules, but they never stand for grams. Stoichiometric coefficients never stand for grams. That's why this problem took so many steps. You can't just go from 1 gram to 2 grams of this. You have to first go through moles. All right, so the lesson here, that was a long-winded way of saying the stoichiometric coefficients cannot be interpreted as grams. Okay, so let me ask you, suppose I asked you, what mass of CO2 can we produce from 60 grams O2? What's the answer to this question? What mass of CO2 can you produce from
Wouldn't it be 41.25?
Yeah, so I just want to make sure that you realize that these are the two ways of asking the same question. Because what are the units for mass?
Grams.
So the first question I asked you was probably a little easier than you would see on the test. They wouldn't actually ask you how many grams, they would ask you what mass, and you would have to translate that into these target units. So I'm just saying, if they ask you for a mass, you have to translate that into target units of grams. So notice, I just want to warn you, you don't measure mass in moles, say. You don't measure mass in moles, you measure mass in grams. Moles are the unit for just amount. They kind of tell you the number of things you have, but they don't tell you the mass. Mass means grams. Those are the standard units in chemistry. All right, so let's erase this. Oops. All right, so let's work this out on paper.
Okay, hold on 1 second.
Take your time.
Okay. What mass? Okay, so first you write target units. That's going to be grams of H2O. You write out what you start with, which is 75 grams of O2. Okay, so first you need to convert that to moles. That's going to be 1 mole O2. Okay, so it's going to be 32 grams over 1 mole of O2. So then, no, sorry. 32 grams needs to be on the bottom. It's going to be 1 mole of O2 over 32 grams of O2. Then you need to change that. Okay, then you need to go. So then there's 1 mole, 2 moles of water for every 2 moles of oxygen. So now cancel out the oxygens, and then you change that to grams. So it's going to be 1 mole of it would be 18 grams over 1 mole. 18 grams of water over 1 mole of water. I got 42.2 grams water.
Okay, that seemed like a good systematic approach. So you were plugging in the units here. Did you slash out the units that were canceling?
Yes.
Good. And I noticed that originally, when you first started here, I think you were first setting up this conversion ratio incorrectly with the 32 on the top. How did you tell that you were making a mistake? Well, maybe it was because you saw the units wouldn't cancel.
Yeah.
So it's perfectly natural for the first conversion ratio not to work. If you force yourself to slash out the units, then you can tell whether the units are canceling or not. So your work should look like this, so that the only units that are left standing are the grams of water. So then we end up with this, and this is our answer. Okay, so that was a good example of how to do that. So you saw that when they asked for mass, what they really meant was grams. Let me just review here. Like, remember I said that when you're trying to figure out the right conversion ratio, it's a little bit, you might just have to use trial and error. Sometimes it's not obvious what conversion ratios to use. One thing I should say is the bottom units should always be obvious. So for example, what units do we put down here?
Grams of oxygen.
That's obvious because we need that to cancel with what's on top. It's a little bit harder to figure out what units go on the top. For that, you might need trial and error. But then once you have this, it should be obvious what units go down here. What units go down here?
Moles of oxygen.
That should be obvious because we need to cancel diagonally. And then you just have to ask, what are other units where I know the conversion ratio that can go up here? And you knew that was moles of water, because we know that conversion ratio of 2 to 2. And then again, you know you're not done because this doesn't match the target units, but these units should be obvious. What should these units be?
Moles of water.
And then you know that you can put grams of water on the top because we know this conversion ratio and because that will get us to the target unit. So I just wanted to point out, maybe you've already seen this, the bottom units are always obvious. It's the top units that are difficult, that might take a little trial and error. Also, now you can see why we were making such a big deal of always writing down the substance, not just the units. You can see these problems would be impossible if we weren't writing down the substances. For example, if you tried to do it like this, without the substances, the whole method doesn't make any sense, because there's a huge difference between moles of O2 and moles of CO2, or grams of H2O and grams of O2. So that's why it's really important in all these chemistry problems to always be writing down not just the units, but also the substance. That's built into the method. I think you've already gotten into the habit of doing that, so that's good. All right. Okay, so let's try this problem.
Okay, so first you would write down your target units, which is grams of H2. You write down what you have, which is 200 grams of NH3. Okay, first you need to convert that to moles. It's going to be 1 mole on the bottom over, let's see, no, sorry. 1 mole on the top over 17 grams of NH3. Okay, then you have then on the second multiplication part, you'd have 1 mole of NH3 on the bottom. No, you wouldn't. You'd have 2 moles of NH3 on the bottom, and 3 moles of H2 on top. Then you have 2 grams H2 over 1 mole of H2 on the bottom. Okay, I got 35.3 grams.
Okay. So yeah, it looks like you're getting the hang of the systematic method. You wrote down the target units and the starting information. Notice again, this problem I was trying to make this more complicated because I gave you the product and asked you to work backwards to the starting material. You were given a certain amount of product and you had to work conceptually backwards to figure out how much starting material we needed. But like we already pointed out in the previous problem, that doesn't really make the problem any harder. It's still just a normal unit conversion. It doesn't really matter whether you're going from product to starting material or starting material to product. So the key thing is, even though this is a starting material, it was still the target units, because that was the thing that was not known. By the way, it looks like one type of problem we won't have time to do today, but it might be obvious to you. You could also go from a given amount of starting material to an unknown amount of the other starting material in terms of grams. You might ask, how many grams of H2 is required to react with 50 grams of N2? Well, you could do that the same way by using the same unit conversion approach. Or if we had two different products, you could say, if I produce so many grams of one product, how much of the other product am I going to get? And it's really the same method using unit conversion. And then you wrote these out. Again, at first, it sounds like maybe some of this first conversion ratio you might have written incorrectly, but you caught your mistake. If you put in the slash marks, right?
Yeah.
Good. What units did you put here?
NH3, sorry.
Good.
Didn't say that.
So then we know that those are going to cancel. By the way, why did you start by doing this? I don't know, but I just wanted to warn you, when you look at the periodic table, people usually say the weight of NH3 is 17 grams per mole. That's the usually way it's interpreted. So sometimes, I see sometimes people get into a bad habit of always putting the number 1 on the bottom. Some people have a bad habit of always putting the number 1 on the bottom automatically, but you can see that's not the way it works in unit conversion. 50% of the time, the number 1 ends up on the bottom, but 50% of the time, the number 1 ends up on the top. So you can't assume that the number 1 goes on the bottom. It just depends on the problem. It only goes 50%. Of course, there's some conversion ratios that don't even have the number 1. Here's a conversion ratio where the number 1 is neither on the top or the bottom. But anyway, I see that a common mistake people make is they just assume that there's a number 1 on the bottom, but that's not the way it works for unit conversion. Anyway, you caught that mistake pretty quickly, and then you went through this. So I was trying to trap you here because I didn't give you a balanced equation, but it looked like you saw you had to balance the equation first. So you did 3H2 and 2 this. So I guess that's where you got these 3 numbers, 3H2 plus 2 moles. So you always have to make sure the equation is balanced, but it looks like you worked that out for yourself. Okay, so here's the conversion ratios that we had enough time to get to today. Like I said, as you study more and more chemistry, you'll just keep adding new things to this table. So this would be a good table to make a nice clean copy of and try to keep adding to this as your chemistry class goes on. As you go on, you're just going to be learning more and more different types of conversions, and it's good to have them all in one nice table. And you can see now how all these things link up with each other. If you're given grams of X, you can use that to find moles of X. Then you can use those moles of X to find moles of Y. And then once you know the moles of Y, you can use that to find the grams of Y. So we were really linking together this conversion ratio and this conversion ratio. This one we didn't need for the problems that we were just working on, but you might need it for other problems. Okay, so it looks like we won't get to limiting reagent, unfortunately, today. But what we were going over is the building blocks for that. Everything we've gone over is a necessary building block for understanding that limiting reagent idea. We did get to some pretty important types of problems here. One thing that's important to realize, I think you've already gotten here, is to realize these problems are not supposed to be super difficult. Once you learn the method, they can become kind of mechanical. Once you get practice with this method, these can start to become pretty mechanical. These are not deep thought or deep philosophy type problems. The way to set it up is to think about the units. So like I said, I would certainly recommend going back and trying to find the time to redo these problems again to make sure that you're not making careless mistakes, because these have to be all very easy for you. Limiting reagent problems use most of these techniques, but the problems are longer. So you have to be able to do this quickly, otherwise it takes too long to do the limiting reagent type problem. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you.